Hi, so we are going to go over section 10.2 and 10.3 in this video. And notice I skipped 10.1. I'm going to leave it up to you to just read the text to get this information because a lot of it is just kind of vocabulary and definitions and just and things that you may be familiar with already. Kind of the same main concepts from 10.1 is that we're kind of skipping over is the type 1 and type 2 errors. So I'll leave it up to you to read up on that. So anyways, section 10.2 and 10.3 are hypothesis tests for population proportions and means, respectively. And so I think the best way to go over this, at least in this video, is to just go over an example and then kind of explain my thought process through some examples. So for section 10.2, which we're going to do first, I'm going to go over problem 15 from page 493, or I'm not sure exactly what page this is, but it's section 10.2, and then it's problem number 15 on Lipitor. And so it's under the 10.2 assess your understandings, the exercises. So anyways, it mentions Lipitor. The drug Lipitor is meant to reduce total cholesterol and LDL cholesterol. In clinical trials, 19 out of 863 patients taking 10 milligrams of Lipitor daily complained of flu-like symptoms. Suppose that it is known that 1.9% of patients taking competing drugs complained of flu-like symptoms. Is there evidence to conclude that more than 1.9% of Lipitor users experience flu-like symptoms as a side effect at the alpha equals 0.01 level of significance? So I just read the problem, and we can see that that there's a lot of information that's kind of standard on hypothesis testing problems that we're going to be pulling out and using throughout the problem. So first off, in any one of these problems, we should have sample data. And with hypothesis testing for population proportions, we should have the Rx. We should have all the information for p hat. So section 10.2 example. So this is number 15 on Lipitor. Yeah, I spelled it right. So anyways, we should have the information on p hat. So we should be given our sample data. Our sample data for population proportion is p hat. That's all the information that we should be able to get from proportion. So what we see is we have X, the amount of successes, or what we consider, I guess, success, out of our total sample size N, which is 19 out of 863. So that I'm just pulling out information. I'm not exactly going through the hypothesis test at the moment, but okay. So anyways, and then there's information. I'm just pulling out the number stuff first. We also have 1.9%, and give you a second to think about what that means. Okay, so 1.9% if in this problem represents P naught. If you don't remember what P naught is, you can look at some examples, but it has to do with the claimed proportion. And in this case, 1.9% is 0.019, 1.9%. So so that represents the claimed value, which belongs in the null and alternative hypothesis. So you may have an idea of where this goes already. I'm just pulling out the information, as we can see. And the only other number that's kind of standard in this type of problem is is the alpha. Alpha equals 0.01 in this case. Our level of significance, and we'll see where this comes into play. So let's go through the steps of a hypothesis test using this information. And so in the text, which should be a few pages back, let's see here. It is on 1, 2, 3, the 4th page of section 10.2, testing hypothesis regarding a population proportion P. So we have these steps that we can go through. This is a good reference on the, I think I said the 4th page of section 10.2 in the purple section, where it says testing hypothesis regarding a population proportion P. There's 5 steps that we go through, and notice that there's 3 bullet points that belong that they talk about before they start the first step, and these are the requirements to do the hypothesis testing. And so the first being, so I'll just call these checks. So the first check, it says the sample is obtained by simple random sampling or the data result from a randomized experiment. And based off of what's mentioned in this problem, when I read this problem, it really didn't say anything about the randomness of the sampling, but if it doesn't say like how they did the sampling, we can just assume that they have a random sampling. So you can just say assume, if it doesn't mention anything about it, assume a simple random sampling. Check. We got that one done. Okay, so we're doing our checks right now. There's the first check. And now the second check, it mentions n p naught times 1 minus p naught is greater than or equal to 10. Now, this should be familiar to you from section or chapter 8, where we need a large enough sample size to have a normal distribution for the sampling distribution. So as you can see, we're using this again. And this should make sense. Well, notice that in chapter 8, we used P naught for this. Or I mean, we used P. And in this section, we're using P naught. The reason we're using P naught is we're assuming P naught, that the claimed value is true. We're assuming that this is true for the time being. So we're using this as you'll see in a little bit where this comes into play again. But so since we're assuming that to be true, we're using that P naught value in our check to see if we have a large enough sample size. So to do this check, we would need to plug in our values. So our n is 863. Our P naught is 0.019, and then 1 minus 0.019. So we calculate this. I'll do that really quickly. 863 times 0.019 times 1 minus, I'm going to put parentheses around this, 0.019, and I obtain 16.09. So is that good enough? So as we can see, 16.09 is greater than or equal to 10. Great. Check. We have a large enough sample size to obtain a normal distribution with the assumed p-naught value. So we're good. So we can assume that we have a normal sampling distribution based off of this size, this value of n, our sample size. So the last check is the sample values. So there's no reason to assume that for this example about Lipitor, that each of the values in the 863 patients, each of those people, their results for if they have their cholesterol levels, if there's no reason to assume that they are dependent of each other. So we can assume that one. So the idea of independence is that we can assume independence, and the reason that we can assume independence because we can assume that one person's cholesterol level does not affect another person's cholesterol level. That's an obvious assumption. So. And the only reason that we would ever assume that there's any dependence in the sampling is if, like, let's say we're using a certain like maybe brother and sister, that then there would be a dependence there because one person may be affected by another because they're from the same family, but they kind of go together, the randomness of the sampling and the independence. So you can usually assume these in most of these problems in the homework. But this, for second check of the sample, the large enough sample size is usually the most common thing that you'll be dealing with in your checks to make sure that you have a large enough sample size to have a normal distribution. So, okay, so we're done with our checks. So we're ready to go into step one. So step one is where we go into the null and alternative hypothesis. So reading the problem, so let's figure out what part of the problem, number 15, that tells us what type of specifically, well, let's start on this. So step one is dealing with our null and alternative. So we always have the same sort of information at first. There's some kind of standard things. So first H0 colon H1 colon, and then since we're dealing with the population proportion, we're always making, we're trying to estimate what P is, so we always deal with the population parameter here. Like in section 10.3, we'll be dealing with mu here. Mu would go here, that's our population parameter. We always have equality here, and then we have some sort of inequality. We'll figure out what that is. And then P naught always goes here. It's the claimed value. So 0.019. And 0.019. Now we just need to figure out the inequality, and that's where we need to look into the problem. So it's based off of the wording of the claimed result. So it mentions here, is there evidence to conclude that more than 1.9% of Lipitor users experience flu-like symptoms as a side effect? So it mentions more. So since it mentions more, we put greater than, more, greater. Okay, so that gives us our alternative inequality in our alternative hypothesis. So now step two, that was step one. Step two is our level of significance. Right there. There's our level of significance. Alpha equals 0.01. Okay, so what we're saying here is that we're going to be testing the claim to see if there's evidence to conclude that it's more than 1.9%. But how picky are we? How picky are we going to be doing this hypothesis testing? Our pickiness is alpha equals 0.01. So this is probably, I guess you can say this is a little more picky than the typical 0.05 level of significance. We want to be even more sure. So you usually want to decide what your alpha is based off of the probability of making a type 1 error. It's the seriousness of making a type 1 error. So that you're not really seeing this so much because they're choosing your alpha for you, but for your labs and for your final project, you're going to be choosing your own alpha. And you're going to be choosing a lot of this information that's given to you in the problems, and you'll be seeing the full use of an entire hypothesis testing from scratch on your projects. So not so much in lab 1, but in your final project, and we'll work up to that. So there's your alpha equals 0.01. Step 2. Now step 3. Step 3 is where we get into the calculations. Step 3 represents our test statistic. And our test statistic always for a hypothesis testing for population proportion is a z-score value, as you may remember. So we call this z-naught for test statistic. Z-naught is our test statistic is always for a hypothesis test. Is what we're doing is we're comparing, we're trying to see how well the sample matches up with the claimed value. So that's why on the numerator of our hypothesis test we have H naught, or sorry, H naught. We have P hat. So our P hat is 19 over 843. How well does our data match up? So how far away is our data compared to our claimed value, 0.019. So P hat minus P naught. How far are they away from each other? But we can't just simply measure the distance from here to here. We got to have, like always with Z naught, we have to divide by a standard amount. So we can figure out how many units it is from here to here. So that's why we divide by, using terminology from chapter 9, we're dividing by the standard error. So that would be the square root of P naught. We're using P naught because we're assuming this is true, the 0.019. So we're using P naught in the denominator because that's what we're using to use for the standard error. So that would be 0.019 minus 1 minus, or times 1 minus 0.019. And then we divide that by n. Okay. All right, so this measures, and if you need help picturing this, it would be good to draw a distribution. I'll do that in a moment on the next page. So you can imagine what's going on here. So actually, I'll write it down here, a really quick picture in a moment. So 19 divided by 843. Excuse me. Minus 0.019. Then we're going to divide by the square root of 0.019 times 63, and I got a value of 0.76. So what this is telling us, Z naught is our test statistic, is telling us that this value here, 19 over 843, our data is 0.76 standard errors, I guess, above our claimed value. So we're trying to test if this claimed value is correct. And what we're doing is we're taking a sample and seeing how well the sample matches up to this to see if this is legitimate, if our P0 is legitimate. So just to picture what's going on, it's always good to draw a picture. So what we're doing is we're assuming that this is correct. So we're assuming that the center of our distribution is 0.019. And then what we're doing is we're trying to figure out how many standard deviations is 19 over 843 from our claimed value. So imagine that we had 19 over 843. Instead of 19 over 843, we had exactly this. So our data matched up exactly with our claimed value of 0.019. Well, obviously, if our data matches up exactly with our P0, then that's giving great evidence that this claimed value is legit based off of our sample. And notice that that the numerator would equal 0 and z0 would in turn equal 0. So we would get a value if we were to standardize this of exactly 0, right in the middle of the distribution. If we were to standardize this distribution, because our P0 would be right in the middle. So I guess you can say our X distribution and our Z distribution, if we had different labelings down here, we would be labeled at 0. That would be the center of the distribution. And so we would be right in the middle if we got our sample data matching up exactly with our 0.019. And notice that if our sample data in turn was really far away from 0.019, like we got 80%, then that would be really bad. And in turn, we would notice that our numerator would be really large or really far away from 0, and we would be way out here on the tails. So if you think about it, if you're really far out on the tails, that's an idea that we're going to be rejecting the fact that our parameter is equal to our claimed value. So that's why we reject, or we fail to reject, H0. It's based off of how well the sample matches up with our claimed value. So we got 0.76. So that's less than 1 standard deviation above. It'd be 3/4 pretty much of the way up above here. So we would expect Z0. We get Z0 to be right here. That's our test statistic. Now we need to figure out how well are we close enough to the tail or not. And so that's where the alpha equals 0.01 comes into play. And remember, if we're doing a right-tailed test, and you can look at your table, and you'll remember that if we're doing a right-tailed test and alpha equals 0.01, then our, if you remember this terminology, critical value, our critical value would be out here at 2.33. So this is the boundary of this would be the boundary of reject or fail to reject. And I'll put FTR. So would we reject H0 or fail to reject H0? Now, as mentioned, it's really bad to have a large value. It's or in other words, it's not looking good for 0.019 if our sample data is really far away from it, and in turn we get a really large z-score, or for our test statistic. So we reject H0, based off our sample if we are beyond the critical value in this case. And we call this z sub alpha for a one-tail, because we're doing a one-tail. It would be z sub alpha over 2 for a two-tail. So, and that's equal to 2.33. If you look up in the back of the book. 2.33, you really can't see that. 2.33. That is our z sub alpha. So as we can see, we're located in the fail to reject region because we're located right here with 0.76. Okay, so there we go. We have failed to reject, and if you remember, this is the classical approach. And so let's think about now so our result for this. I'm running out of room. I'm going to write it over here. We are going to fail. So we're done with step 3. Step 3 is just calculate the test statistic and the critical value. We did that. So step 3 is done. Step 4 is to compare. And this is step 3 and step 4 of the classical approach. So since our test statistic, is larger than smaller, way smaller than the critical value. And as you remember, we got 0.76 is less than, and that's z naught, equals 0.76, which is less than 2.33, which equals our z sub alpha. Since z naught is less than z sub alpha, and we're doing a right-tailed test, then we, so since the tested statistic is smaller than the critical value, and we fail to reject H naught. Okay. All right. So, and I gave you that that flow chart. Okay, so where we left off, we're going into step 5 of this hypothesis test, and step 5 is our conclusion, where we state our conclusion. Now, whenever you state your conclusion, especially, well, it's just a really good reference. The hypothesis test flow chart that I attached to my Labs Plus. Well, yeah, I attached a PDF. And anyways, the first step of the flow chart is, does the original claim contain the condition of equality? So the original claim is where we determined the sign for the alternative hypothesis. We determined that's a greater than sign. So we can use that here. Note, and I'll read that claim again. Is there evidence to conclude that more than 1.9% of Lipitor users experience flu-like symptoms? So notice it says more than. That's not equality. That's an inequality. So you would say no for the first step of the flowchart. No, the original claim does not contain equality. So, so in that case, we would go down on the first step of the flowchart. The second step is, do you reject H naught? This one's pretty straightforward. And this, in step 4, remember that we failed to reject H naught. Since we failed to reject H naught, we are not rejecting H naught. So no again. So we have a no and a no from the flowchart. No, no. So that gives us the fourth option for the wording of the final conclusion. So step 5 is the conclusion, and that wording should be, there is not, I'm just reading directly from the flowchart. there is not sufficient evidence sufficient sample evidence to support the claim that, and then it says ... original claim, if you read that last step of the flowchart. So now, at this point, we just need to pretty much copy and paste the original claim right in here for the remaining part of the sentence. So the original claim is the claim that more than, we would just go directly to that sentence and we would go to more than 1.9% of Lipitor. This is directly from the problem in the middle of that sentence where it states the claim. The Lipitor users experience flu-like symptoms as a side effect. And this is kind of up to you, but I really like this where you mention at what level of significance. And so a side effect at the, we're going to just explain how picky we were, alpha equals 0.01 level of significance. Okay. So there is not sufficient sample evidence, and since there's not sufficient sample evidence, if you look up the definition of if it's statistically significant, is another way of saying it. It is not statistically significant, so there's not sufficient sample evidence, and so that's telling you that you are in the middle of the distribution, and of the bell curve, and that's in the fail to reject region. So whenever you have a fail to reject, you say there is not sufficient evidence. So if you read the second option of the wording, where the other fail to reject, it also says there is not sufficient evidence. But the wording's different because the first step, if we would have said yes here, it would set up the wording so that we are addressing inequality in our claim, because we want to copy and paste our claim right in there at the end of the sentence. And what we're prepared for is not equality. So that kind of changes the wording a little bit. From the step 2 is there's not sufficient evidence to warrant rejection. And here we're saying there's not sufficient sample evidence to support the claim. So little difference of wording, but it makes a big difference to make the sentence flow correctly. So it's a really good flow chart. I would suggest using it. I got this from a different book. It just works really well, and I think it's really easy as soon as you get used to it. If you took the class with me last term, then you, Math 243, you're probably used to it already. And anyways, continue using it, and you'll be able to use it all throughout this term. So anyways, yeah, so that is the example of a classical approach. And I really want you to get used to the p-value approach, which is where we're dealing with comparing p-value to alpha in step 3 and 4. And so step 3, you calculate the p-value, and then step 4 is you compare the p-value to alpha. And in this case, just to explain the p-value approach, let's go ahead and do that really quickly. So back to step 3. If we were going to do step 3 p-value approach, we would want to, okay, so we're going to use z0 equals 0.76, and we're going to find a p-value. So that represents the probability of being on the tail compared to our test statistic. So we're going to find the probability that Z naught, that Z is greater than 0.76, which is Z naught. So kind of a picture of this. So what we have is we have a value of 0.76, and we want to find the probability or the area of all the everything to the right of 0.76. That's one way of saying it is the probability that a z-score is greater than that value, 0.76, because greater than represents the area on the tail. So what we're going to do is we're going to look it up on a z-score table. So that is the probability, or sorry, we can look this direct. Well, we can do 1 minus the probability that z is less than 0.76, since the z-score table gives you the area to the left. And looking this up on the z-score table, let's check it out real quick. We have 0.7764. So we have 1 minus 0.7764. So the area to the right would be the complement of 0.7764, which is 0.2236. So that is the area on this tail, 22.36% of the entire area under the entire curve. So is to the right of 0.76. So there's our p-value. So if we're going to compare our p-value, now what we're interested in is, remember, you want to keep into consideration, I'll just draw a picture again to kind of refresh and see it again. The idea is everything, since we're doing a right tail test, anything to the right is in the rejection region. Reject H naught. And anything over here to the left is fail to reject H naught. So keeping that same idea as from the classical approach, but thinking a p-value is, okay, so if the p-value approach, if the p-value is further to the left, that means your p-value is increasing, because the area to the right, as we move the the z naught to the left, will increase our p-value. So imagine that we have this critical region, or in this case 2.33. The area to the right of 2.33 is alpha. So what we want is, if we're going to be failing to reject, which we already know since we already did the classical approach, but if we have a p-value that is larger, if the p-value is larger than alpha, we then fail to reject, because we would be our value would be in the fail to reject region compared to 2.33. Okay, so that would be the p-value approach, and that would be step 4 when we compare. So hopefully that makes sense. Let me know if it doesn't, but you'll have homework on this where you have to compare the p-value to alpha, or at least calculate the p-value and compare them in some way and determine if you fail to reject or reject based off this information. So there's the p-value approach and the classical approach. They're just different, depends on what you prefer. I will make you do the p-value approach to make sure you understand it and verbally explain it for your final project. So be ready to do that, and let me know if you have any questions on the p-value approach. So as we can see, we are failed to reject, since the p-value, 0.2236, is larger than our alpha, 0.01. Okay. So, and then of course we would go to step 5, and it's just the same conclusion. We're done. All right. So 2 different approaches. They're both legit. And every time, if you do the classical approach or p-value approach, you'll always get the same result in regards to fail to reject or reject H naught. So they agreed with each other. We were failing to reject in both approaches. Okay, and now let's go ahead and go to an example of a hypothesis testing of mu, of our mean. And let's go ahead and hopefully we don't find another example of a right tail test. Let's let's see here. Yeah, let's go ahead and do problem 15 of section 10.3. The effects of alcohol in the brain. So, all right. So section 10.3 example. So section 10.3, we talk about the effects of alcohol in the brain. So in a study in the American Journal of Psychiatry, researchers wanted to measure the effect of alcohol on the development of hippocampal region of adolescence. Hippocampal, I don't know. The hippocampus is the portion of the brain responsible for long-term memory storage. I might be saying that word wrong, sorry. The researchers randomly selected 12 adolescents with alcohol use disorders. They wanted to determine whether the hippocampal volumes in the alcoholic adolescents were less than the normal volume of 9.02 cubic centimeters. An analysis of the sample data revealed that the hippocampal volume is approximately normal with X bar equals 8.1 and S equals 0.7. Conduct the appropriate tests at the alpha equals 0.01 level of significance. So as we can see here, let's pull out the information like we did in the last problem. So with a mean test, a hypothesis test for population mean, we have different types of data. We're not given a p-hat. That's a sample statistic based off of a gathered sample for a proportion. In this case, the sample statistics would for mean would be X bar and S, right? The sample mean is sample standard deviation. So we have X bar equals 8.1 and S equals 0.7. And we have alpha, our level of significance, of 0.01. And the other piece of information we need is our sample size that gathered this X bar and S, how we got this information, which is very important, as we know. The researchers randomly selected 12 adolescents, so N equals 12. So it's kind of nice here. It actually says in the problem, the researchers randomly selected, so we got our steps of randomness, just to point that out. But anyways, we have all the numbers that we need. But let's proceed. So here's our checks. We're going to go pretty quick through this because it's not really much different. There's some slight differences. So randomness. Do we have randomness? So it says in the problem, the researchers randomly selected 12 adolescents. So I'll just say randomness check. Now, if you remember from chapter 8, we're not dealing with NP 1 minus P is greater than or equal to 10 because we're not dealing with a proportion. To determine if we have a large enough sample size for this problem, we need at least 30, right? But let's see here. But what's kind of convenient is, remember from the check, either we need n is greater than or equal to 30 if we have a non-normal distribution, or we need any sample size, even 1, 2, 3, up to whatever value you want, 1 to infinity of sample size, and as long as you have the original distribution is normal. So as you can see here in the problem, it says, an analysis of the sample data revealed that the hippocampal volume is approximately normal. It tells us it's normal. So, normal original distribution. It says it in the problem. We found out that our sample data is normal. So that we can assume that our population is normal if our sample is normal. Okay? So our original distribution is normal. So we have a large enough sample size. We actually don't even have to check the sample size because we know we were dealing with a normal distribution, not a non-normal distribution. So we're done with that. And lastly, independence. So as you can see, this is almost identical to the checks for a proportion, and we can assume that each of the 12 adolescents that were randomly selected, each one is independent of each other. So independence, we're going to assume to be true. So we're only assuming this one. So we're assuming independence. This is given to us. They say that it's randomly selected, and we know it is normally distributed. So we don't have to assume these. We know that they're true, but we have to assume independence. Okay? And this is a pretty reasonable assumption, considering it's just, in general, it's always an assumption that you can make, because independence is almost always, it never really failed to be obtained. So let's continue, and now we're ready to do our hypothesis test. So step 1 is our null and alternative. So as mentioned before, we have H naught, always, H1, alternative, colons, mu, because our population parameter, in this case, since we're measuring mean, is mu. We're dealing with mean, not proportion. Okay? And we deal with equality here always. Oh, and one other value that we forgot to pull out of here is our mu sub naught, our claimed value of our proportion. And that being 9.02. Forgot to mention that. So that goes right here, 9.02, 9.02. And now, are we dealing with a left, right, or two-tailed test? So we read in the problem, they wanted to determine whether the hippocampal volumes in the alcoholic adolescents were less than the normal volume. Less. Left tail. All right, so read it in the problem and you can determine what you're dealing with. Okay? So there we go. There is our there is our null and alternative hypothesis. Step 2. Now we have alpha. Our level of significance, 0.01. It's given to us in the problem. Step 3. Now this represents the test statistic in all of our calculations involved. So our test statistic, I'll just put TS. Now, if you remember, similar to Chapter 9, we're not following a standard normal distribution. We're not dealing with Z anymore, with a mean, measurement of mean, because we don't know sigma. We know S. So it follows a T distribution. So our test statistic is a T naught. And as you may remember, T naught is equivalent to the comparison, and now we're, like 10.2, we're assuming that our claimed value is correct. So we're centered at 9.02. So that goes right there. So we're comparing it to 9.02, our claimed value. How well does the sample match up to our claimed value? So in this regards, we would want to compare 9.02 to 8.1. And we will get back to that.
How's it looking? See?
Wow, that's good. I like it. Very good.
They're tablecloths. Table placements. That'll work, huh?
Yep. Okay, and we would be dividing by s by the square root of n, like that. And so we would calculate 8.1 minus 9.02. So the numerator, just the numerator, 8.1 minus 9.02 is negative 0.92. So that's telling us that that our sample data, or the average of our sample 8.1 is almost a whole unit below the claimed value of 9.02. So it's not exactly the same, but we wanted to determine how many standard deviations or standard errors we are from the claimed value 9.02. So that's why we divide by the standard error. So we would divide by 0.7 and root of 12. So it is 4.55, approximately 4.55 standard deviations, or standard errors, sorry, below the claimed value. Our sample data is. So the sample obviously is pretty significantly far away from our claimed value. So it's pretty obvious that we're going to be rejecting H naught. I can just tell right off. Hopefully you can see that too. A lot of us, that's a significant t-score. Oh, sorry, we're dealing with T naught, so it may not actually be. So actually, let's compare this to our critical value. That's where we need to do calculate our critical value at this point. So our critical value, so negative. Hopefully you can see negative 4.55 is not actually that significantly far when we're dealing with t-scores because we have fatter tails. So we need to check that. So our degrees of freedom in this case is 11. Remember, degrees of freedom is our sample size minus 1. So we'd look up 11 on our table, and then and that would tell us which row we're on. And then we would want to look up 0.01. Where are you? Right there. So I have a value of 2.718. Since we're doing a left tail, that would be a critical value of negative 2.718. Okay? So as we can see, this is significantly far away compared to the critical value. So as you can see, maybe a picture of this. A picture will help you determine how to what happens in step 4. But as we can see, our critical value, let's just say that's 0, and we're down here at negative 2.718. Negative 4.55 is in the critical region, on the tail. So that will tell us that we're going to be rejecting. It's always the same. Reject is on the tail, significantly far away from 0. In the middle is close to 0. That would be in the fail to reject region, at the FTR, fail to reject region. Okay? Reject H naught, fail to reject H naught. In this case, negative 4.55 is out here, further away from 0. So our test statistic is in the critical region. Okay? So we're rejecting H naught. Okay, so I'm going to leave it up to you to determine the p-value, and I'm going to make this example a little shorter, doing the p-value approach. But as we can see from step 4, that we are that our test statistic, for step 4, our test statistic, I'll put TS, is further away from the 0. In this case, since we're doing a left tail, our test statistic is smaller than our critical value. So we will be, this implies that we reject H naught. Okay? We're rejecting H naught because the test statistic is on the tail compared to the critical value. Okay, so that tells us that how to word our step 5. So first off, remember the flow chart. Does the original claim contain the condition of equality? Since we're doing a left tail test, you should be able to see that that would be a no, because we have a less than. It's so let's see here. So the second part of the flow chart, it says, do you reject H naught? That would be yes. We reject H naught. So the wording for this, I actually lost my page because I went to the T table. Let me pull this up really quick. We're in 10.3. And we were going over example. There we go. Effects on the brain, number 15. Okay, so here we go. We have a no and a yes. So we go down and then up. So we're on the third option of the wording. So the sample data supports the claim that the sample data supports the claim that, and then original claim. So we just copy and paste our original claim to make sure the sentence flows. So the sample data supports the claim that the hippocampal volumes, campal levels or not levels, who cares, volume in the alcoholic adolescents were less than the normal volume of 9.02 centimeters cubed. And then if you want at the alpha equals 0.01 level of significance. That is a solid conclusion. The sample data supports the claim that the hippocampal volumes in the alcoholic adolescents were less than the normal volume of 9.02 centimeters cubed at the alpha equals 0.01 level of significance. Okay. Hopefully you're getting this flow chart down, but I did the classical approach for this mean example. Go ahead and try to see if you can understand the p-value approach for rejecting H naught. And just to quickly show you the different tests that you would do using your TI-83, you can do this really quickly. You can go to stat, and then you go over to tests. And if you were to do a proportion problem, a hypothesis testing for proportion, we would go down to one prop for proportion and one representing one variable, z-test, since we're doing a hypothesis test on proportion, one variable. So for our previous example, we were doing a right tail test. So we would go to right tail greater than p naught, and our p naught value, if you remember from our previous example, our p naught was 0.019. And our x was 19, and our n was 863. Go ahead and check that example again, and we would calculate, look at earlier in the video, and you'll see that those would be our values. And as you can see, we got the same, actually, what happened? 863.019. 0.258. Wait, where am I? Let me make sure I entered this in correctly. Test 1 prop z test 0.019. It's a greater than. So according to this, we get the following test statistic, 0.649. And I got 0.76. If you remember, I'll go back to this really quick. 0.76 in our calculation for our test statistic. And here we got 0.649. And let's just double check here. 19 divided by 843 minus 0.019. And then we divide, let's go ahead and you can see this a little better. Oh well, I can see it. That's good enough. Second square root of 0.019 times 0.01 or 81 divide 863. 0.76. What is going on? The right tail does. It doesn't make a difference. 19 over 843. Why is this value so far off? So this is, yeah, I'm doing these live. That's okay. Not live, but just winging it. Why are we doing this? 0.019. That is correct. And 19 and 863. It's a right tail test, which should make a difference for test statistic. Calculate 0.649. We use. Am I actually disagreeing with the calculator? Because I feel like we are doing this correctly. 10.2. Maybe they're using a different calculation, which wouldn't make sense. Oh, they're using a calculation. This really isn't making sense to me. Why am I getting a different? I'm checking the book. Alright, let's check this one more time. I don't know what is going on here. Wow. I do not know what I did wrong, but now I'm getting the right answer. Okay. Apparently, well, not the right answer, but what they're getting in the calculator. I don't know what I did wrong before, but I'm getting 0.649. But it does not change our conclusion. We're still well into the fail to reject region. Sorry about that. I don't know what happened. Yeah. So that's 0.649. I'll put some remarks in the beginning of the video that fix or mentions that my mistake. So sorry about that. All right. So anyways, that really doesn't affect too much. Apparently I made a calculator error. I'm human. Oh well. All right. So if you have any questions, please let me know. These were two examples of hypothesis testing involving proportion and mean. So I'm going to make a new video, and so we're done reviewing chapters 8 through 10 from Math 243. I'm going to make a new video, separate video on standard deviations. We're going to be doing confidence intervals and hypothesis tests for standard deviation. So that will be new. You have not seen that in Math 243. So anyways, let me know if you have any questions.